So now, which of the following is false? A, population-based methods carry out multiple local searches at once. B, the time is the number of individuals or local searches times multiplied by the minimum time of the local search find. All right, is that better? There. All right. How are we going for time here? Does everyone need more time? No, no. Okay, let's stop that. Oh, that's exciting. Good. All right, let's go through these in some sort of order. B. So what happens, we're carrying out lots of multiple searches. We're carrying out K local searches at the same time. We're carrying out K local searches. Right, so there's K things going along all throughout this thing. And what happens when we find the solution? We can stop, right? So this one we can stop here, and even if all of these go on forever, the time we take, we're only going to secondly time, this is the time we're going to take, right? Does that make sense? So we're carrying out K local searches. As soon as one finds a solution, we're going to stop, so it's going to be K. So the amount of work we're going to do is K times the minimum, okay? So the amount of work is K times the minimum. All right, what's other? D. It's more likely a population-based method will find a solution in a local search with no restart. If you remember the graphs that we did, so if you remember the graphs that we did this, that found out, and we sort of had some percentage of things, there was no solution. So with no restarts, we often get to be no solution. Right? So if you often get to this stage of there's no solution, so the probability is P that there's no solution, the probability that all of them have no solution is much bigger. Right? So the probability that 10 things have no solutions is much less likely. So if the probability that one search will not find a solution is P, the probability that K searches will not find a solution Who remembers? You don't have to remember the formula. We remember the formula. They all have to fail. So they fail with 1 minus P And so that they all have to fail, so that's 1, but then they succeed is 1 minus that. And if you work this out, if P is a half and K is 10, it fails with probability about 1 in 1,000. Right, so it succeeds 99.9% of the time. Right, so if we do run, even if half of them succeed, only half of them succeed, we have 10 of them, they fail, and 99.9% succeed. I think you learn this in grade 11 in school, that if you keep producing things, the fact that the probabilities keep going down if you do this. Okay, so what was that one? That was D. So D is true. Right, so in fact this is dramatically so. Right, so this dramatically drops down. And E is the right answer here. Population methods are not guaranteed to find a solution because they're not guaranteed to sort of be able to escape these local minima. Right? This is not 0. This is not 100%, right? A log gets close, log can get closer to it, doesn't reach it. So this is guaranteed to find a solution. So the answer here is E. Any questions? I like these questions like this because then we get to cover things we otherwise wouldn't. All right. I think that's the only one. Oh, one more. Which of the following is true? A, if an algorithm is above and to the left of another algorithm in the runtime distribution, it's always faster. B, a random walk cannot escape a local minimum. C, the amount of time taken per step is about the same for all local search methods given modern data structures and the speed of computers. Or D, carrying out arc consistency before doing a local search can reduce the search space. I don't know which is true. Only one of them is. Yeah, which is true? Who needs more time? Okay, do you still need more time? Okay, let's do 5, 4, 3, 2, 1, stop. Right, D is the right answer. A is sort of an interesting question. A is interesting because what happens is because these are often random, right, so even if one is like this and one's like this, on average this is better than the other one, right? But some of the times this goes really fast and some of the times this goes really slow, right? Some of the time this one doesn't find a solution and some of the times this goes fast. So it's not always the case that it's faster. If you look at the distribution, it's better. Okay, so that's important to know here. When you have this one here, this blue one is above this one, but some of the times this goes fast, and some of the times this goes slow. Okay, does that make sense? And that's what this tells you. This tells you that some of the times this goes fast, and some of the times this goes slow. And if it always is faster, then there's sort of one is always to the left of everywhere. So if one is like that and the other is like that, whoops. If it's like this, if this is to the left of this, then this blue line, this one is always faster than this one. Right? Does that make sense? Okay, any questions about that? Okay. All right, so what we're going to do today is we're going to start off talking about logic and inference. And as far as we're concerned, logic is just a different way of doing constraint satisfaction. What we're going to do is we're going to write this funny little language called definite clauses. We're going to talk about the semantics of propositional logic, and we're going to maybe get to talking about bottom-up and top-down proof procedures. So we're going to actually automate this, because I know people have studied propositional logic, but we're going to look at it sort of from a slightly different perspective, because we actually want to state facts about the world and automatically prove them. And what we did before is we defined an interpretation in constraint satisfaction as assignment of values to all the variables. So it's interpretation, remember, we assigned one value to all the variables. And a model is an interpretation that satisfies all the constraints. So interpretation and models are things you should remember what they are. And a proposition is either true or false in an interpretation. So a proposition is something that's either true or false in an interpretation. It's just going to be some statement that's either true or false in interpretation. Yes? Propositional, there's a whole lot of symbolic logics. There's first order predicate calculus and there's other languages. Propositional logic is just has ands, ors, and nots and atomic statements. It's a very simple language. In fact, I'm even going to do a simpler language than propositional logic. But what's different now than we did before for constraint satisfaction is often we don't want to just find a model, but we want to know what's true in all the models. So what we're going to do is talk about statements that are true in all the models that always are true. We might have particular variables we want to query about, want to know about some particular variable. And we might have other questions like, why didn't the light turn on when I flicked the switch? It's sort of a question we're going to be able to answer with the logic-based representations we're going to do. And we'll also have more compact and modular representations for these constraints. So not only are we going to have these sort of tables or less than, we're going to have languages for specifying constraints that's modular and compact. And it's actually a useful representation we're going to talk about. So that's sort of how it relates to constraint satisfaction. So there's a whole lot of reasons why we're going to use propositions. So they're often more natural than filling out tables. So we don't necessarily just want to, when we did the constraint satisfaction things, we filled out tables. It's often better to write logical formulae. It's easier to check their correctness and debug them. We'll talk a little bit about how to debug when you make a mistake, how you debug them. We can incrementally add them. And also we might only have partial knowledge of some of the constraints. And we might want to say, is there something we can prove even though we only don't know everything that's true? Okay, so some of the reasons are about representations. Some of the reasons are about asking queries. We actually want to query particular atoms. We'll ask queries of what follows in all models. And it might be more complicated than just asking a value for the variable. We're actually going to consider asking what-if queries. So in fact, to answer the question before, what's wrong with, why didn't my light turn on, we're actually going to prove a more complicated query. We're going to show, that maybe if the switch was down, then the light was off, is something that might follow. Or if it's broken, something that might be off. So we're going to prove that. So we have flexible languages. We can exploit the fact that things are only true and false, can make things much more efficient reasoning than we had before. And we can extend it to when we have the first order predicate calculus, we sort of have infinitely many propositions. We have infinitely many infinitely many of these algebraic variables, so we actually have to reason about infinitely many variables. So there are infinitely many integers, right? And there might be a property of each integer about whether it's a prime number, but we can still represent it. There might be arbitrarily many people and courses. We still want to reason about people and courses. That's why we're going to introduce this language that extends it. Okay. So here's the general idea about what we're going to do is we're going to have this idea of semantics. We're going to start with some task domain that we're going to represent. Then we're going to choose some atoms, and a human being's going to choose atoms to denote things, and they're going to have meanings to this person who's designing this knowledge base. So we're going to have this, so we're going to choose atoms. Then we're going to tell the system about the domain, we're going to answer the questions. And the system is going to be able to tell whether something is a logical consequence, something that follows from all of this. But me as the user can actually interpret I have meanings associated with atoms. And so that's going to be the trick we're going to use is that I'm going to have meanings associated with atoms. I'm going to put them in the computer, and we're going to get at answers, even though the computer doesn't necessarily know a meaning. On knowledge base, we're actually going to define it in a second. I just want to give a big picture. Yeah, Prolog is a language that's a logic programming, is a language that's an extension of what we're going to do. So if anyone's doing 3.12 at the moment, you'll probably be bored by the next few classes. That's a warning, yeah. But you might not be. We're doing a few different things because we're actually not treating it as a programming language. We're actually going to ask, some of the times we're actually going to ask different questions than sort of Prolog lets you do. So here is this sort of domains. There is a domain we might do of a smart home. You might model my electrical switches in this house, and you might be able to answer questions like, how do I make L1 lit? And the sort of question we're going to do is you can put down switch S2. It's going to tell you how you can make it lit. Or if you observe that L2 is not lit and your model says it should be lit, you could ask why is it not lit, and maybe there's a fault, the light's broken, or some switch is broken, or some circuit breaker's open. So we're going to be able to answer. This is the sort of domain that we're going to think about now, is this sort of domain. And given a world like this, and here we've already given names to wires and lights and things, which your house doesn't come named, but you just make up names for things. That's what we're essentially going to do. We're going to make up names, and they have meaning to us. And we're going to have, and in the user's mind, if you look at the top right, you might have a symbol called light 1 broken, and that means that light number 1 is broken. We might have SW up, meaning the switch is up. And I have these symbols. So I'm going to reason with these symbols like power, meaning there is power in the building. Unlit light 1 isn't lit. Light 2 is lit. So I have these symbols. In my mind, they have meanings associated with me because I know what they are. And in my computer, I'm going to tell it things. This is a funny language we're going to write down with ifs and ands. So light 1 is broken if the switch is up and there's power and it's not lit. So it's broken if the switch is up, there's power and it's not lit. Might be the switch is up, there's power there's power in the system if light 2 is lit. We might know that light 1 is unlit and that light 2 is lit. And this has meanings associated with it, right? This is actually, to us, this has meaning associated with it because we know about this light 2 and whether that switch is up and which switch we're talking about. So we have meanings associated with these things. But then we're going to tell the computer the things on the left, and the computer's going to come back and say, light 1 is broken. And the computer doesn't know the meaning of the symbols on the right, but we have meanings in our heads. So we're going to write down things. We're going to have the computer, we're going to tell it things, it's going to give us conclusions. And the computer doesn't know the meaning of the symbols. However, I can interpret this symbol because I have meanings to the symbols. Yeah.
When we ask the computer a question,
yes?
Are we essentially asking the computer to prove or disprove answers to that question?
Yep, that's what we're going to do. That's what we're going to do. We're going to prove things and disprove things. But this is the reason we're going to do it, right? Because we have meanings. We have a computer that's just going to do symbolic computation, but we can interpret the meanings. This was a Philosophers wrote centuries about this, and this is sort of the solution, is that you have meanings in your head and you can compute these things and we can interpret the answers according to our meaning. But the computer just does symbol manipulation, it doesn't know the meanings, we're going to prove things. Okay? So here's our very simple language. Just propositional definite clauses. We have an atom is a symbol that contains letters, digits, and this underscore that starts with a lowercase letter. So that's the atom is just some name. Fred, Mary, Harold, something, Light, 7, things like this. So body is either an atom or a conjunction of bodies. So it's going to be you can conjoin things together. So we just have bodies. So definite clause is an atom, or as a rule of so an atom is just a name. So a body is either an atom or a conjunction of atoms. A definite clause is of the form, it's just an atom, or is the form atom left out where there's a body. And a knowledge base is a set of definite clauses. A knowledge base is a set of definite clauses. Okay, does that make sense? People sort of understand that. The easiest way to do this is to let's do this and we'll show at the same time. All right. Just to make sure everyone knows what's going on. I should wait for it. All right. So the answer is either A, B, or C. And A means yes, no, and B, C means I'm not sure, can review the definition. So then we can, if it's all obvious, we'll go quickly. If it's not obvious, we go slowly, right? Does that make sense? Is the following a definite clause? So just the healthy by itself. Is healthy by itself a definite clause? So a definite clause is either an atom or an atom if a body. So the question is it a definite clause, this healthy? How are we going? So why isn't it a definite clause? Come on, someone tell me why it's not. Yeah.
Definite clause is an atom with a body.
No, it's either an atom or it's an atom with a body. This is two things. And a body is one of these two things. And a definite clause is one of these two things. It's either an atom or it's an atom with a body. Yeah.
It is a definite clause because it is an atom.
Yeah. So why is everyone saying B? Ah, that's better. Are there any questions about that? The answer is A. Right? Okay, I'll stop that. All right, next one. Happyeth healthy. I should wait a few seconds, shouldn't I? Peer pressure is dangerous things, you know, you guys. Don't just... All right, how are we going here? Peer pressure tells you to do A, but is that right? Yep, that's a definite clause, right? Good. Next one. X. Who remembers the definition? Yeah, it's not. The answer is B, it's not. It's got to start with a lowercase letter. Lowercase letter? Okay, good. Oh. What about sad? All right, you should do this quick. We should do this in 10 seconds. We should be able to do it. Yes, it's not. Sad's not, doesn't start with a start with a small case letter. When we start typing them in, the system will make it, will care. That's why you're doing this. All right, good. So happy if healthy and rich. Is that one? Yes. Right, good. This is a definite clause, sort of classic definite clause with a head and a body with a conjunction in it. Okay, next one. Come on. What about healthy and rich? Is that a definite clause? Let's see how peer pressure is getting us. It could be wrong, you know. Is it one of these? Is it an atom or an atomy of a body? It's not a definite clause, right? Because we're only allowed to have, this might be body, but it's not a definite clause. So we can't write just A and, we can't write happy and rich. We're not allowed to write that in this language. Okay, what about happy if healthy or rich? Can we write that? Are we allowed to write this? Are we allowed to, is it a atom if body, and where a body is an atom or a conjunction of atoms? Is it? Is healthy or rich in the conjunction of atoms? So why is everyone saying yes? Peer pressure is getting to you guys. Don't believe them. Yeah, thank you. Right, this is not a definite clause. We can't write ors on the body. We're very silly language. It's very restricted. It's extremely restricted language we're going to do. Okay, we're not allowed to write that. We're only allowed a conjunction, right? We're only allowed ands in the body. Okay? Questions? What about, oh, let's cross this out. Let's do this other one. What about healthy and not rich if you're happy? We're allowed to write that. And the answer is no, we can't write that. We can only have an atom in the body, in the head. And what about this last one? The bottom one here, happy if healthy and not rich. Can we write that? Is that a conjunction of atoms? So the atom's just a name, yeah. Oh, you're just doing stretching. You can stretch. I'll ignore. This is not. The answer is no. You're not allowed to write not rich. Not rich is not an atom. Right? We're not allowed to write this. We don't have negation in this language at all. It's a very dumb language. It's a very silly language, right? The answer here is no. Right? You can't write not rich. Okay, all we can write is these things like happy if healthy and rich. This is the sort of thing we can write. It's a very dumb language, okay? Okay, any questions about that? No. You can tell when I grade them, I actually click on the letter and say that the right answer is. Not anymore. I could probably go back and do it, but I don't remember what the answers were. All right. Any questions about that? So you know what the language is now, right? It's a very dumb, silly language. We're going to do silly languages because A, they're useful, and B, we can actually do something more complicated with them. So now we're going to do an interpretation. I is going to assign a truth value to every atom. So it's going to say whether one atom was true or false. And a body is this this body B1 and B2, because the only thing we have in a body is just conjunctions of things. So a body is true if B1 is true and B2 is true. So you remember the normal truth table for and, that's all we have for bodies. A rule, H if B is false in some interpretation, if B is, the body is true and H is false. Right, so we have this, so H if B, so if H is B and then H if, whoops, H if body, right, so if they're both true, and true, then this is true. And it's only false when we have, what's does it say there? It's false if B is true and the head is false. Otherwise, it's going, all the other cases, it's going to be true. Right? So this is an if statement. What's the other one? False, false. False, false is true. Does that make sense? Just the truth statement of an if. Yeah.
So this is basically like a conditional but in reverse.
Yeah, this is a conditional inverse. This means head, red head, if body. It's equivalent to body if head. We're going to write it the other way around because we're weird. Well, we're weird because we're going to treat these as, when we interpret them, we're going to end up interpreting them in different ways. It's just a very silly language, right? It's just the reverse definition of ifs. But it's an if. It looks like an if. This, if, this. It's just implication going that way. You should get used to implications going all sorts of ways. OK, make sense? So a model of a, oh, what did we do all that? Right, and a knowledge base is true if every clause in it's true. It's interpretation. So a model of a set of clauses is an interpretation in which all the clauses are true. So that's what we did before. A model is just an interpretation in which all the clauses are true. And if KB is a set of clauses, so it's this knowledge base is just a set of clauses, and G is some conjunction of atoms, then G is a logical consequence. And we're going to use this funny turnstile, meaning G is true in every model of the knowledge base. So we're going to use this funny KB models. G means G is true in every model of KB. So the last one there says that, so this one there says there's no model in which G is false. So the last one's just saying this in the same way. So G is true in every model, so there's no model in which G is false. Okay, so that's the definition we're going to give of logical consequence. This is called logical consequence. Okay. So let's do this. So here's the knowledge base. P if Q, Q, and R is F. And R is true if S is true. Okay, so now we have, and here are 5 different interpretations. So interpretation here assigns a truth value to every P, Q, R, and S. And so the question is I1 a model of, so I want A, again, A, let's do, A means, let's write this. So we're going to do it. A means yes, B means no, and C means huh. Okay. Meaning, I don't know, please explain it again. Because no one pressed C before, so I didn't have to explain it more. Okay. Oh, I think we stopped. I think we did that. Wait. Let me do that for C. All right, so what's the answer? Is I1 a model of KB? So is every clause in there true? Yes. Right? Every clause in there is true because the heads are all true. So it must be, right? Good. So it is a model. Oh, I think I ought to stop that. Or what about I2? Is I2 a model? Everything is false. Right, it's not a model. Why is it not a model? Because of Q, right? Q's got to be true for it to be a model. Okay. So there's a clause in the knowledge base that's false in this interpretation. Okay. So it's not a model. What about I3? Is I3 a model? PQ. Is I3 a model? Oh, let's see what it says. Right, it is a model. P if Q is true, Q is true, and R if S is true. So it is a model. Okay. The fact that no one pressed C means you don't. Okay. So it is a model. What about the next one? Oh, stop this. Start this again. What about I4? Is it a model or not? Whoops. Is it a model? What did people say 15 seconds in? Right, it's a model. Each of the four clauses are true in there, right? Because if S is true, because R is true even if S is false. Okay? So this is a model. And let's do this. What about I5? Is it a model or not a model? Right, why is it not a model? Because R if S is false in here. Okay? Everyone happy now? You know what models are? Okay. Now I want to know which of P, Q, R, and S logically follow from this knowledge base. So let's look at, whoops. Same question. Is P true in all the models? Actually, I should have asked. Is P true in all the models? So the first question is P true in all the models? Is there a model in which P is false? Q is true in every model, and P is true whenever Q is true, so Q must be true in every model. Right? Does that make sense? So the answer is yes. So the knowledge base logically entails P. Okay? What about Q? Let's stop this again. Actually, don't go around. Is Q a logical consequence of this? It should be easy for people, hopefully. Oh. You've got to watch out for peer pressure. It's been wrong before, you know. So Q must be true in every model because the second statement says that Q is always true. So if the second statement is true, then it must be a model. Okay, so the second statement there that says Q is true, the second statement. So in every model, for that to be true, Q has to be true. Okay. Let's go up to here. What about R? I'll stop this. Is R a logical consequence? Does R logically follow from it? What's the answer here? And the answer is no. There is a model in which it's false. We can see one there, namely model I3 is a model in which R is false. Okay, so there is a model in which it's false. I3 is one of them. And therefore, we should be able to do the last question easily. What about S? Oh, stop this. Right. S is not a model. Okay, there's a model in which it's false. I3 is such a model in which it's false. Okay, let's stop that. All right, are there any questions about that? So now what we're going to do is, we'd like to have this. So why we do all this funny semantics is, what we'd like to do is we'd like to choose some task domain which is the intent. So my view of the user's view of it, they choose some task domain which is the intended interpretation. They can associate atoms with propositions they want to represent. So you can associate an atom with a proposition you want to represent. Then the user is going to tell the system clauses that are true in this intended interpretation. Sometimes we call this axiomatizing the domain. We're going to tell the system that's true. We're going to tell the system things that are true. Then we're going to ask questions, and we're going to interpret these questions that are as though they're about the domain. And then, if the knowledge base logically entails G, then G must be true in the intended interpretation because it's true in every model of the knowledge base. Okay, so if we have a particular knowledge base where we mean particular things for symbols, then that's a model for the knowledge base. G is true in all of them, so G must be true. So it says yes, then G must be true. If knowledge base doesn't logically entail G, then maybe the model of the intended interpretation is maybe the intended interpretation is the one model where G is false. So we don't know whether G is true or not. Okay, so if it logically follows, it must be true. If it doesn't logically follow, we don't know whether it's true or not in the intended interpretation. But because they have meanings associated with symbols, they can answer they can interpret answers with respect to their meanings. So we now have meanings associated with things. So here's this domain again. And one of the things we can do is we could write down statements that are true in here. So here's sort of an axiomatization of how this world works, right? I have meanings associated with light L1, light L2. And I can say that L1 is, if I look at the top right, I can say L1 is lit if the wire W0 is live and L1 is OK. And W0 is live if W1 is live and switch S2 is up. So if we look back here, so it says L1 is lit if there's power coming into W1 and L1 so L1 is lit if there's power coming into W0 and L1 is OK. There's power coming into W0 if switch S2 is up and there's power coming into W1. Right? We can axiomatize, write down rules about how this world works. Okay? And we have meaning associated with these symbols, right? We can sort of check them. We can read this on the top right and check whether it's true in our world. Right? So we have meanings associated with it. The computer, however, doesn't have meaning, has any meaning associated with it. All it knows is the knowledge base. However, it can determine if something's a logical consequence. So it can do a simple manipulation to work out if something is a logical consequence. And I don't know, as the computer, it doesn't know if knowledge base entails G, G must be true in the intended interpretation. So I can say, yes, it's true. And if it's not, doesn't, and if this knowledge base doesn't entail G, then there's a model of the knowledge base in which G is false. As far as the computer is concerned, this could be the intended interpretation. So because we have meaning associated with it, we can answer logical consequence queries. We can say, in here we can say, answer questions about what must be lit in here. And And we can actually answer questions saying that L2 is lit, because we actually wrote down rules in there. We say L2 is lit. So as far as we're concerned, L2, we can prove that L2 is lit, and we have meaning associated with these symbols, and we can now answer questions. We can interpret these answers with respect to our meaning. Okay, so that's why how this funny game goes of having meanings, and this is why we sort of use logic in this way, because we have meaning associated with symbols, but the computer just does symbol manipulation. We can interpret them with respect to the meanings. Okay, any questions? All right. All right, let's stop there and have a good weekend.